All right, today we're doing something a little bold. We're putting one of the biggest ideas in all of physics on trial, space-time itself. The question is the reality that we see actually the reality that is? Let's dive in.
So let me ask you something really fundamental. When you look at the world around you, are you actually seeing it as it is right this second? Imagine you're on a high-speed train, just zipping along. You glance down at your own shoes. From your point of view, they're not moving an inch. They're just there. Seems simple, right? Well, this is exactly where things start to get weird.
See, the thing is, light doesn't travel instantly. For you to see your shoes, the light reflecting off them has to travel that short distance to your eyes. It's an incredibly tiny delay, for sure, but it's not zero. You're never, ever seeing your shoes in the present. You're always looking at the past. And that tiny little crack in our perception is where this whole investigation really begins.
So, before we can challenge the champ, we've got to understand the champ's moves, right? And that means we need to talk about the established map of reality, Albert Einstein's special relativity, a theory that's built on one absolutely revolutionary idea. So, back in the day, the classical view was pretty simple. If you're on a train and you throw a ball, its speed adds to the train's speed. It made sense to think light worked the same way. But Einstein comes along and drops a bombshell. He said the speed of light is the universe's ultimate speed limit. It's constant. It doesn't matter if you're standing still or flying in a rocket, you will always measure a beam of light moving at the exact same speed. This one idea changed everything, leading to all that mind-bending stuff like time dilation and length contraction. But what if that's not the whole story? The source material we're digging into today throws a wrench in the works. It suggests that maybe, just maybe, there is an absolute frame of reference, a kind of master compass for the entire universe. And it uses this brilliant analogy called deviation shooting. Think about it. To hit a clay pigeon, you have to aim ahead of it, right? You aim where it's going to be. So the model asks, in one of Einstein's famous thought experiments with a light clock on a moving train, why wouldn't the same logic apply? Shouldn't you have to aim the light beam at where the moving mirror will be? Why would light get a free pass from the laws of moving targets? The absolute heart of this whole argument is this. Light isn't just traveling in a featureless void. It's traveling through a specific medium, the electromagnetic field. And in this view, that field is the absolute stage. It doesn't move, it doesn't change. It means all motion ultimately is relative to this one field, not just relative to other people. Now, this way of thinking leads us to a concept that is, frankly, one of the wildest I've heard in a while. It's called temporal thickness, and it's all about rethinking what it even means to see something. Okay, let's unpack that, because it's a mouthful. You look at a room and your brain tells you you're seeing one single, perfect snapshot of now. But this theory says, nope, what you're actually getting is a collage. It's a mosaic of light particles that all left their starting points at totally different times. Let's try to picture this. Okay, let's build this idea up. We start with you, the observer. Your single moment of perception, your now, we'll call that time 0. T equals 0. Now, the light from your shoes, or the screen you're looking at right now, has almost no distance to travel to get to your eyes, so it comes from the very recent past. Let's call this layer T-1. But then, you look up at the moon. The light hitting your eye left the moon over a second ago. A distant star? That light could be thousands of years old. That's from the deep, deep past, T-10 or T-1,000,000. And there it is. Your one single moment of seeing is actually a composite image made from all these different layers of history. Your present isn't a razor's edge. It has thickness. So this is a really cool idea, but how on earth could you actually test it? Well, the model lays out a pretty clever thought experiment designed to see if we can separate Einstein's reality from this new idea of objective reconstruction. All right, here's the lab. Picture a big 60 by 60 by 60 cube. Inside, we have a tiny train, just 4 units long, and it's moving fast, 10% of the speed of light. At the exact instant of our experiment, at time 0, this train is perfectly centered in the cube. And here's the key. We have camera eyes plastered all over the walls of this cube, and even on a sphere inside the cube, all of them just sitting there, waiting. Their only job is to record exactly when and from what direction they see the light from the train. And this is where it gets crazy. Just look at the data. Remember, at time 0, the entire train exists at once. But that's not what the cameras see. Camera A, which is off to the side, sees the light from both ends of the train arrive at almost the exact same instant. Okay, that makes sense. But look at camera B. It's in front of the train, so it sees the light from the front of the train a full 4 seconds before it ever sees the light from the back. Every single camera gets a totally different, warped version of the event. So, if every observer sees a different story, how do we ever find the truth? We work backward. It's like cosmic detective work. Each camera takes its 2 pieces of data, when the light arrived and what direction it came from, and calculates a sphere of possibility for where that light signal could have started. And here's the magic. When you take the spheres from all the cameras and you overlay them, there's only one single point in space-time where they all intersect. And that intersection, that's the objective truth. That's the train as it really was at time 0, completely free of any one observer's distorted point of view. Now, this is already a pretty wild ride, but here's where the story takes a very 21st century turn. The person who came up with this didn't just publish a paper. They took both of these models, Einstein's and this new reconstruction idea, and they presented them to our new modern oracles, a whole suite of advanced AI. They asked the AIs a straightforward question: which of these models is a better description of physical reality? And the results? Well, they're kind of stunning. As you can see, the vast majority sided with this new model. And Einstein's standard interpretation, it got exactly 0 votes. Not a single one chose it when given this alternative. So what's going on? Why did the AIs vote this way? Well, it seems they really liked the model that treats seeing as a messy physical process. It describes a reality where information is delayed, where data is incomplete, and where the truth has to be carefully reconstructed. Which, if you think about it, is a lot closer to how complex systems, from your GPS to the AIs themselves, actually have to figure out what's going on in the real world. Which leaves us with one heck of a final question, doesn't it? Is reality the immediate, distorted, time-layered image that just hits our eyes? Or is the true reality an objective thing that we can only ever know by gathering clues from all over and carefully, mathematically building it back together? Maybe what you see is just the rough draft. The truth might just be in the calculation.